Welcome to The Explainer. You know, in the world of AI, there's this constant mantra, bigger is better. More parameters, more data, more compute. But what if that's not the whole story? Today, we're diving into a paper that throws a massive wrench into that idea.
So let's just cut right to the chase with a question that sounds, well, a little crazy. Can a 7 billion parameter model really go head-to-head with something as massive and powerful as GPT-4o? I mean, on the surface, it sounds impossible, right? We're talking about a model that's just a fraction of the size.
Well, believe it or not, the answer is a huge, resounding yes. And the proof is right here on this chart. That bar, the R7B model, isn't just competing with giants like GPT-4o and Gemini. It's actually scoring higher on average success rate. This isn't just an incremental improvement. This is a totally different way of thinking. So let's unpack exactly how a smarter workout routine can build a champion AI that beats out the heavyweights.
All right, here's how we're going to break it all down. First, we'll look at the big problem they're trying to solve, the AI Agent Chasm. Then, we'll get into their two-part solution, the AgentGym-RL and the ScalingInter-RL method. After that, we'll check out the mind-blowing results, and finally, wrap up with the big takeaways for all of us in the field.
Okay, so first things first. To really get why this paper is such a big deal, we need to understand the problem they're up against. What's the massive challenge in training AI agents to be, well, actually useful in the real world?
You know, the core issue really comes down to a lack of the right infrastructure. For a long time, the AI community just hasn't had a standardized interactive playground, a place where an agent can truly learn from scratch through trial and error, reinforcement learning, instead of just being spoon-fed pre-curated data, which is what we do with supervised fine-tuning. And that lack of a proper training ground has some serious consequences. Most of the current approaches are kind of stuck in the kiddie pool. They're good for simple, single-shot tasks, but they're often unstable to train, a real pain to optimize, and they're almost always leaning on that supervised data crutch. All of this just holds agents back from learning how to think on their feet through actual interaction. So, to fix this, the researchers basically decided to build the ultimate training facility for AI. It's called AgentGym-RL. And honestly, the best way to think about it is exactly like a state-of-the-art gym, but for AI agents. Now, if we want to get a little more technical, what AgentGym-RL really is a unified end-to-end framework. The key words here are modular and flexible. It means you can easily swap out different components, plug in a new agent model, a different virtual world, or a new learning algorithm without having to rebuild the whole thing from scratch. It's a huge deal for researchers. And this gym, it has everything. We're not just talking about treadmills and weights. It's got a whole suite of specialized training zones. You've got web navigation for learning to browse real sites, deep search for research tasks, digital games, and even embodied tasks where the AI controls a virtual robot. It even has a lab for running scientific experiments. It's incredibly diverse.
But look, you can have the fanciest gym in the world, but without a smart workout plan, you're not going to see results. And that brings us to the second, and maybe even more important innovation here, their training method, which they call ScalingInter-RL.
The core insight here is just so intuitive. It's this idea that you don't learn to swim by getting thrown into the deep end of the ocean. The paper says it perfectly. The goal is to let the agent adapt to the environment in stages. It's all about progressive overload, just like in a real workout. So here's how this workout plan actually works. You start the agent with really short interaction rounds. Think of it like learning basic chords on a guitar. This lets it master the fundamentals, what researchers call exploitation. Then, once it's got those down, you gradually increase the number of turns, making the tasks longer and more complex. This forces the agent to think ahead, to plan, and to try new things. That's the exploration part. The end result? A much stronger, more stable agent that doesn't just give up when things get tough. And this progressive approach is so important because the alternatives just don't work. If you only train on short tasks, the agent gets good at the easy stuff, but then it just plateaus. It never learns to strategize. On the flip side, if you throw it into a super complex, long task from day one, it might get lucky a few times, but eventually the training just completely collapses. It's too hard. ScalingInter-RL is all about finding that Goldilocks zone, that perfect, gradual ramp-up in difficulty.
All right, so the theory sounds solid, right? A great gym, a smart workout plan, it all makes sense. But does it actually work? Does it build a better AI? Let's get into the results, because this is where it gets really impressive.
And this really gets us back to our starting point. Look at these numbers. A 7 million parameter model trained with their method hits almost 59% accuracy. Meanwhile, a massive Llama model, 10 times larger at 70 billion parameters, is stuck down at 47%. Let that sink in. This is a massive win for smarter, not bigger. It really suggests that the compute we spend after the initial pre-training on this kind of reinforcement learning could be way more impactful than just throwing more parameters at the problem from the start.
So let's break that down. How does it perform in specific domains? Let's start with Web Arena. This is a super tough benchmark that makes the AI do things you and I do online, like shopping, managing a website, or using maps. And look at this. The 7B model gets a 26% overall score, which is a full 10 percentage points higher than GPT-4o. This proves it can navigate the messy, unpredictable world of the live internet, which is a huge hurdle for AI agents.
Okay, what about moving around in the world? In embodied AI, where the agent has to control a virtual body, the story is the same. On the Baby AI benchmark, which is all about following commands like go to the red ball and pick it up, the ScalingInter-7B model sets a new state-of-the-art record. This is so important because it shows the training is helping the model connect language to physical actions. That's a critical step if we ever want capable robots in the real world.
And to really prove this isn't a one-trick pony, let's look at scientific reasoning. In the SciWorld benchmark, it's the exact same story. Another new state-of-the-art score, blowing the old one out of the water. This is a big deal, because SciWorld requires abstract thinking and using scientific tools within the simulation. So what we're seeing is a broadly capable agent that excels not just in one area, but across a whole range of very different and very difficult challenges.
Okay, let's step back and look at the big picture. What should we as developers and researchers really take away from all this?
There are a few huge takeaways here. First, and most importantly, technique matters more than size. This shows that smart reinforcement learning can help smaller open-source models punch way above their weight class, even competing with the big proprietary giants. Second, that progressive, scaled approach to training isn't just a nice-to-have. It's absolutely critical for getting stable, effective results. And finally, it reminds us that the environment design is key. RL thrives when an agent gets clear, consistent feedback on its actions.
But let's be real, it's not a silver bullet. And to their credit, the researchers are really transparent about this. There was one specific task, a complex chemistry simulation in SciWorld called ChemMix, where every single model completely failed. We're talking a score of 0 across the board. It's a humbling reminder that we're still a long way from solving complex, multi-step scientific reasoning.
Ultimately, this paper feels like it's opening a brand new chapter. It's shifting the conversation away from the brute force approach of just build a bigger model, towards a more nuanced focus on how do we build smarter learners. It proves that the right training environment and the right method can unlock incredible potential. And that leaves us with a really exciting question to ponder. As we get better at teaching these agents how to learn for themselves, what's the next great frontier they're going to conquer?